shown the superconducting quantum system, which two major companies which are working on that are IBM and Google. And on the right, I have showed a trapped ion quantum system. Many companies are working on that system as well, but the most major one is IonQ. And so the goal is that we want to connect a different quantum computers over long distances. And the reason behind that is that will allow us to do neat things such as secure quantum key distribution and distributed quantum computing. But to connect to different quantum computers or quantum systems, we need a quantum channel which will carry the quantum information from one system to another system. Now, for the quantum channels, there are a lot of work is being done on that. For example, this very recent work from Waldorf Group from Zurich, in which they connected two superconducting quantum systems using a cryogenic link. So this whole tube you see in the middle is also at low temperature, millikelvin temperatures, and they use microwaves to send the information from one system to another system. Now, this is an impressive system, but as you can see, like this is very rigid and is not scalable. So if you want to scale the quantum networks to like hundreds of kilometers and more, what you want is a photonic link using optical fibers. The system is scalable and it requires ambient condition. So it can work at room temperature and we don't need to cool the whole system down. But there are some constraints associated with the photonic link. It's quite popular, like we use the optical fibers for current technologies as well. And the idea is same. The attenuation, like the losses in the fiber, the optical losses is minimum at 1550 nanometer, which is famously known as like telecom band. So what we want is, we want the telecom photons to carry the information in the optical fibers. But the issue is most of the quantum work happens in the visible regime as denoted by these dots. Now the issue, the thing which happens is like when you go to longer wavelengths, the losses is dominated by IR absorption due to multi-phonon coupling, whereas at smaller wavelengths, the losses in the fiber is dominated by Rayleigh scattering. So both are pretty fundamental losses. So like chances, and it's pretty established technology. So chances that this will change is pretty small. So that's the first constraint. And the second is the second hardware component which we need for networks is network end node. So what a network end node is, it connects different quantum networks, and that's the very last node of it. And there are few requirements to be met to build a quantum network end node. So it should be a small scale quantum processor, combining robust storage of quantum information with a link to quantum channel. Now, as I described just earlier, that the quantum channel would be based on telecom photons. So the first thing which we need is a Qubit-photon interface. This interface will convert the quantum information from flying qubits, that is telecom photons, to stationary qubits, that is in our devices. And this example is based on diamond. So this is the electron spin of a color center. Now, what other thing we need is a memory qubit register. So the difference between memory qubit and a normal qubit is that memory qubit has 10 or more times the coherence time of the communication qubit. The reason being that we need the coherence of the qubit to be longer than the time needed for the entanglement generation. Now, this entanglement generation is asynchronous, so it happens and it over a slightly longer time, and so our memory qubit register should hold that quantum information for long enough. And the third one is just high fidelity control, so that we can take care of any errors which comes during the operation. So we should be able to do fault tolerance or error correction on our network node. Now, my work focuses on just this small part of that is Qubit-photon interface. So what we actually do is our goal is to transduce the quantum information from flying qubit, that is telecom photons, to stationary qubit, that is a spin in our case. There are other promising system as well. People are trying to do it with trapped atoms and other system with quantum dots. But I'll just share like why I think our diamond-based approach is the most promising one. So coming back to it, like why diamond? So what you're seeing here is a synthetic 3x3 millimeter diamond chip, and that's how the diamond chips look in lab. It's very small. Work is being done on increasing the size of these chips, but right now we are limited by 3x3 millimeter. The first important property for diamond is that it's wide band gap. It has a large band gap of 5.5 electron volt. What it means is like it's transparent from ultraviolet to radio, from like 225 nanometer to 20 micrometer. And it also has a relatively large refractive index and low dispersion. What it means is like we can confine photons inside the diamond really good. The second important point is, and the most important one is like it hosts color centers with spins. So traditionally, diamonds came in various colors. Even you will find these in jewelry shops, and chances are the diamonds with color are pricey than the transparent ones. But these color comes from the defects in the diamond. And for example, this orange one has a nitrogen defect in it, and that's why the color, it has an orange color. Now, it turns out some of these defects are excellent systems. It acts as a natural trapped atom, and these systems can have a coherence time of up to 1.7 milliseconds at room temperature, which is like really amazing. And they're optically active. By that, I mean like you can use just light to initialize and read out the spin states. The third important factor with diamond is it's the material with highest stiffness known to us, like known to human, and with a Young modulus of 1200 gigapascal. So what it allows us to build high frequency resonators. And the reason we need high frequency resonators is it becomes easy to cool down them to quantum ground state. As you will see, like I'll show you the diamond resonators we have made. And the last one is the solid state system. It offers like scalability. We can mass produce whatever system we are making. So we have nano device fabrication techniques, which involves lithography and etching. It's pretty industry-wide system, which is like silicon transistors are made using this approach. And what this allows is like we can build quantum controls like optical control, optomechanical control, even the magnetic and RF antenna lines in a way that is scalable. And we can also fabricate the defects, which are the colors, and you can associate them with spins. So we can also fabricate the defects using these approaches. So let's now focus on the color centers in diamond, because that's what we'll be discussing most of the time. So the most popular two color defects in diamond are nitrogen-vacancy centered in diamond and silicon-vacancy centered in diamond. So for nitrogen-vacancy is a spin-1 system, and it has a, as I mentioned earlier, spin coherence of around 1.7 millisecond at room temperature. And silicon-vacancy is slightly worse in that case, as we get only a 0.3 millisecond of spin coherence, and that too at low temperature of 100 millikelvin. And both are excellent single photon sources, and you can, as you can see, both are in visible range. But the reason, like some of the time we prefer silicon vacancy despite their low currencies is because of their inversion symmetry. Sorry. What it allows us to do is we can put these silicon vacancies in nanostructures without degrading their quality. Whereas if you put nitrogen vacancy in nanostructures, their quality degrades rapidly. So even with low coherence time, sometimes silicon vacancies are preferred. And they have enabled a lot of state-of-the-art experiments ranging from sensing, quantum networking, and they are the leading platform as of now. So let's come back to like what we do, and that is Qubit-photon interface. And I'll discuss the early work a bit, and then we'll focus on what exactly is our approach. So this work is relatively new, still was published in 19 and 20 by looking group from Harvard. So what they did was they implanted a silicon vacancy center in diamond in a photonic crystal cavity. So what this is, it's just a cavity as I represented here. So the issue is like the interaction between a single photon and a single spin is very weak because of the size of the both photons and the spin. So if you put them inside a cavity, that you increase the chance of photon interacting with the spin by many folds. So using this approach, you can interface photons with the spin system. Now, a key figure of merit for quantum interface or transducers is cooperativity, which is defined by the coupling rate between the two systems squared with the ratio of decay rate of each system. So if it's spin photon, if it's spin, it's its coherence rate. And if it's photon, then it's decay rate. The loss is outside the cavity. So for a system to be useful, what we want is C greater than 1, because that enables coherent interaction between two quantum systems. So you can interpret this C as the probability of coherent interaction between two quantum systems. So what we want is C to be always greater than 1. So in this work, the photon spin cooperativity was 100, which is quite amazing, and it's an impressive work. But as you can see, there are some challenges associated with this work, that it works at 737 nanometer. Now, there are quantum frequency conversion techniques which you can employ and convert the 737 nanometer to 1550 nanometers, but that's not the only challenge. So the whole challenge is that for a qubit-photon system interface to work, the qubit should have a narrow and stable optical transition, and that too preferably in telecom wavelength range. Now, there are many quantum systems like gate-defined quantum dots, superconducting qubits, they don't have optical transitions at all. And whereas nitrogen-vacancy centers, as I showed you earlier, they suffer from spectral diffusion. So that's the zero phonon line of NV. So the primary optical transition of NV in bulk diamond, you can see it's like very constant with time. But as you put the NVs in nanostructures, the white dots are all over the place and scatter. So you can't build an interface if your transition is fluctuating that much. So to overcome this issue, what many researchers all across the world, what they are doing is they're trying to find an intermediary which couples with both qubit and photon. So luckily, mechanical resonators do that. So there's a lot of work going on which are trying to couple superconducting qubits with mechanical resonators, spin qubit with mechanical resonators, even quantum dots, and as well as photons. And this establishes that the mechanical resonators are in universal transducers and they can be interfaced with any system. So now, instead of just building a qubit-photon interface, we are trying to build a qubit-photon interface intermediated by phonons. So that's the whole idea behind my project. So let's now discuss a bit about qubit-phonon interface. So a lot of work was already done in which they coupled the first two parts. So like this work from Fuchs group from Cornell, they used a piezo transducer to induce stress in the bulk diamond. And they did that and controlled the NV spins coherently. JH group from University of California, Santa Barbara, and Meletinsky group from Bessel, they used nanomechanical resonators and did the same. Whereas Wang group from Oregon, they used surface acoustic waves to control the NV spin. So we build upon these works and we demonstrate a qubit-photon interface that is mediated by phonon. So we use nitrogen-vacancy centers in diamond and cavity optomechanics. So let's just follow the transduction scheme first. So what we do is we couple the telecom photon to phonon via cavity optomechanics, and then phonons get coupled to spin qubit via stress coupling. So this is a typical schematic of our system. This is a diamond optomechanical resonator. We call it a microdisc. And we couple the light into the microdisc and out using a tapered optical fiber. So we bring the optical fiber next to the microdisc and couple the light. And we drive the mechanics of this optomechanical resonator using the light. And turn out this mechanics induces stress. The stress is maximum at the center. And this is stress then drives the spin qubit. And from now on, we will discuss this work. So let's go a bit deep into the nitrogen-vacancy center in diamond. So I gave you a brief description of nitrogen-vacancy earlier, but this is a slightly detailed energy level diagram of nitrogen-vacancy. And I would like you to just notice at 3 key things. The first being, we use a green laser to excite the ground state to the excited state. And the fluorescence between ±1 and 0 state is spin dependent. What I mean by that is, once you excite the 0 state to 0 using green, 0 state fluoresces more because the ±1 state has this extra non-radiative channel which it takes. So if your state is in ±1 state, you will fluoresce less. And if you are in 0 state, you will fluoresce more. And that's how we read out which spin system we are in. And if you shine your green laser for long enough, what it happens, it cycles the spin states. And as you can see, the ±1 state comes back to the 0. So if we shine the green laser long enough, we can initialize our spin state to the 0 state. And as you will see later, that ±1 states are mechanically coupled, and that's what we do with Hertz stress. We drive the transition from -1 to +1. This is how the data looks like. So what you're seeing is a time resolved NV fluorescence histogram. On x-axis, we have time, which is like 6.4 nanoseconds per bin. So, and you can see as we shine in the green laser and start collecting the fluorescence from the NVs, we see a dip if we are in ±1 state, and we see a peak in 0 state. And that's how we know, okay, which state we were in. So moving on, now we'll just focus on the ground state, that is this part of the NV. So usually the ±1 states are degenerate, but you can split them using magnetic field parallel to the NV axis. And in our case, NV axis is this Z axis. And the ±1 state and 0 states are split by D, which comes from spin-spin interaction, which is around 2.9 gigahertz. So we can transfer the population from 0 to -1 and 0 to +1 using microwave fields, which are basically just AC magnetic fields. And the first step we do in our experiments is optically detected magnetic resonance, which is famous by ODMR. What we do is, it's quite simple to follow. So as I told you earlier, that +1 and -1 state, they read dark, and the 0 state is bright. So as we scan our microwave frequency, the moment we hit on resonance with either of the states, we see a dip because we collect less fluorescence. So you can see at 0 magnetic field, we see one dip. And then as we increase the magnetic field, we see the ±1 state splitting. And that's what we do. Now, the reason we split is we drive the transition from -1 to +1 using our stress. So what we want is this to be on resonance with the stress frequency, as you'll see later. So let's quickly discuss the dynamics of time dynamics of our NV ground state system. So since our NVs are embedded in the optomechanical resonator, this is the SEM of our resonator, and nitrogen vacancies are implanted everywhere. And the ones we work with are at the center of the microdisc. So you can see that the nitrogen vacancy center, they have a lifetime of around 0.8 milliseconds and a coherence time of around 0.7 microseconds in our case. And we use microwave field to do the Rabi oscillations between the 0 and -1 state and 0 and +1 state with our Rabi frequency quite high. And this results in the pi pulse length of around 50 nanoseconds and 200 nanoseconds for each transitions. So now let's come back to the stress. So what we actually do is the perpendicular AC strain, it drives the +-1 transition. And this whole dynamics can be explained by the Hamiltonian ground state Hamiltonian of NV. The first one is just the splitting between 0 and ±1 state. The second one is Zeeman shift. The third, this one, third and fourth represents the stress dynamics, and the last two are for the microwave coupling. In our work, we drive this stress using our fundamental radio breathing vibrations of the microdisk. And the how we do it comes from the cavity optomechanics. So cavity optomechanics in general is just enhanced coupling of light to phonons. So we have an optical cavity where you can, this is a canonical representation where the other mirror, you can think of it as it moves with a mechanical frequency of omega. And that's how the whole dynamics is governed. This is one of a typical example of a microcavity, so no mechanics. And you can see they also use a waveguide to couple the light into and out of the microdisk. And that's how a typical cavity scan looks like, which is the cavity frequency in this case is at visible range, and the FWHM determines the losses of the cavity. Now coming back to our diamond microdisk, so these devices are fabricated by our own device, our own group, and our fabrication recipe is even followed by groups from Harvard and MIT. So we had fabricated this diamond microdisk quite a long time ago, like 4 years ago. And this is a typical cavity transmission. As you can see, it's centered in telecom range and has a quite high quality factor. What you're seeing here is we are sensing the thermal motion of this microdisk, and that also has a quite high quality factor and is in around 2 gigahertz. So our mechanics and optics are coupled via optomechanical coupling, which is around 25 kilohertz. And the cooperativity in this case, as I told you earlier, that cooperativity tells you how good an interface it is. So we are talking about photon-phonon interface is around 3, which is of course larger than 1 and what we want. The reason we get this high cooperativity is because cavity optomechanics allows us to parametrically amplify this coupling rate by the number of photons we put in the cavity. And diamond allows us to put a lot of photons because it's transparent, as I told you earlier, and it's also very thermal conductive. So we can put around 10 to the power 6 photons. In silicon, you won't be able to put even, like you would put a lot less photons. So now, this is a simulation where we show the stress per phonon. So in our system, we have 1 kilopascal per phonon of stress. This is this is the state of the art, but still quite low. So it only translates to spin phonon coupling of 10 hertz, which is quite low. So what we do is, so like we are here, but spin dephasing rate is quite high. So what we want is our spin phonon coupling rate to be around the same ballpark with the spin dephasing rate. So to do that, we laser our phonons. The way we do is we blue detune our laser by omega m, that is the mechanical frequency, and via Stokes process, it creates a huge influx of phonons. And as we increase the laser power, as you can see here, and once we cross the threshold, we start lasing the number of phonons. So from thermal phonons, we go to 10 to the power 8 phonons, and that translates to maximum stress of 21 megapascal, which is good enough to drive the NV spins. And that's how our experimental setup looks like. You can see the objective with the magnet to split the ±1 state. This is the piezo stack that has a spatial resolution of 50 nanometers. So we move that to couple our fibers and everything. You can see the fiber pigtail using which we couple the light into our device. That's where you see the diamond chip sitting right there. And this is the optical microscope. So we use a copper wire as a microwave antenna. And these are hundreds of microdiscs on one chip. We work with only one, the best microdisc. And you can see the optical microscope. So this is the tapered optical fiber. That's the microdisc. And we use this tapered optical fiber to couple the light into the microdisc and output. This is NV photoluminescence scan. So this scan is made by the NV fluorescence. We scan our objective, and you can see the microwave antenna as well as the optical fiber in this with the microdisc. So that's how our system looks like. And so let's come to the final final, how we detect that we have controlled the spins using stress. So as I told you earlier, we initialize our spins using green laser to 0 downstate. Then we apply a microwave pipe pulse, which sends the spin population from 0 to +1. Then we wait for some time where the mechanics acts. And it drives the population from +1 down to -1. And now it's the readout. So what we do is we bring, since the +-1 state, they have the same fluorescence, we can't just read out. So we have to deploy a different reading out mechanism. So we bring back the -1 state down to the 0 state, and then we read out. So if mechanics would not have driven any population here, we won't gain anything. So when we read out the 0 state, we gain a signal, and we repeat the same system when we bring down the +1 state, and we lose the signal. So yeah, to repeat, if mechanics won't work, would not have worked, we won't gain any signal, and we won't lose any signal in +1. And that's exactly what we see in our work. When the stress is on resonance with the spin mechanics, when the stress frequency is on resonance with the spin splitting between +-1 state, we see the population from +1 state going down, and the spin population driven to -1 state going up simultaneously. So this confirms that, okay, we are driving the population from +1 to -1. And on fitting this data, we determine our optomechanical spin driving rate of around 200 kilohertz, which is what we expected, as I showed you earlier. Now, currently our system is bit limited because NVs are not as good as they have a their strain susceptibility is quite low. So in future, what we are trying to do is boost the spin mechanical cooperativity to around 1. Right now, it's like 10 to the power -9, which is quite small. Our mechanics and photon cooperativity is already larger than 1. And we also want to do a spin-phonon coupling rate of around 1 megahertz. So this can easily be done if you just replace the NVs with SIVs, because SIVs have like 10 to the power 5 times the spin susceptibility as compared to nitrogen vacancies. But we also want to do some changes to our optomechanical resonator design. So other groups like JH from UCSB and Longkar from Harvard, they have already fabricated optomechanical resonators. Their design is slightly different, but they have fabricated, and we estimate around spin-mechanical cooperativity of around 100 and optomechanical cooperativity of around 10 to 10 to the power 4 with the current technology. We have also just made like optomechanical crystals. So this is the CM of the device we have fabricated, and you can see that it has a phononic shield as well. So phononic shield helps reduce the losses of phonons. So phonon doesn't escape this way. And I hope we'll reach the cooperative regime that we have discussed in our paper quite soon. And we are also thinking of doing the same thing with other hybrid platforms, but they are like, their novelty come from that they are 2D. So similar to hexagon boron nitride, they also host defect centers, and they are also quite good. Again, the one of the criteria we need is like there should be wide band gap that is transparent in from visible to telecom and beyond. And since they are 2D, they are less, the quality of the spins degrade quite less, and you can atomically precise on which layer you want the defects and all. So that's also a work in progress other than the diamond. And so yeah, to summarize, Qubit-photon interface is a key hardware element to realize a practical quantum network. And we have demonstrated an interface between spins and telecom photons and at room temperature. And our approach does not involve intrinsic optical transitions and can be adapted to many other solid state spin qubits. So from diamonds, and even there are upcoming color centers in silicon carbide, which are also quite good. So it can be used with that system as well. So in the end, I would like to thank you for your attention, and also my group members who helped me in this project. And yeah, like if people are looking to apply for MSc or PhD equations, you can apply to this group. So thank you.
See, Prasoon, can you remind me a little bit about that zero width phonon?
Zero phonon line?
Zero phonon line. Yeah, zero width.
Yeah, so usually what happens is, I'll just go to the, yeah. So this 637 nanometer is the zero phonon transition. But what happens is, as you go to a different orbital states, the orbital states on the top are shifted at a longer radius. So they are not quite on top. So as you have the, so what happens is there's a huge phonon sideband. So the light comes from the excited state down to the ground state, but to a phonon sideband, vibrational phonon sidebands, which are here. And then they trickle down to the spin states. So all the quantum network protocols, they only work with the zero phonon lines, because that's where you can, like the photons are indistinguishable. And so phonon sidebands are disregarded. So for NVs, only 4% of the light coupled to the zero phonon line. Rest of it is in phonon sidebands.
Okay. Okay. Yeah. Thank you. Very nice talk. Really enjoyed it. Thanks.
Thank you. Yeah. Thank you. See ya.
Okay, good night, all of